Next speaker is Daniele Durante, talking about Bayesian modeling of networks and business intelligence.
Great, so thanks everyone for coming and thank you for the introduction. I would also like to thank the organizer for this kind of inspiring workshop. It's quite exciting to be here and be one of the speakers. So now, going to my talk, and in line with the topic of this workshop, I will also deal with networks in a specific application. So it makes sense to start by immediately entering this application, the type of data that we have, and the type of problem that we want to answer. As you can guess from the title, this is related to business intelligence. And in particular, we are working in an insurance company. And this company is administrating 130 agencies, and each one of the agencies is selling the same type of 15 possible products to its own customer. Of course, there exist many different types of customer. In this talk, we are particularly interested in two subsets of them. The monoproduct customers, so these are customers subscribed to just a single product for the moment. And then we have the multi-product customers, who are customers subscribed to multiple products. And essentially, what we want to do is try to define cross-selling strategies targeting the monoproduct customer and offering to them an additional product in order to motivate these guys to become multi-product customers. Why do we want to do that? Well, mostly because there exists a strong competition in many markets, in the insurance one in particular. So for a company, typically, it can be a good idea to focus on its own customer base and try to have many multi-product customers. Why this? If they buy many products, they give us more money, but of course. But if you want to see from another perspective, if they buy many products, they are more tied to the company because they need to face much more switching costs if they want to move from our company to a new one. So this is what actually we want to do. And statistically speaking, essentially what we want to do is for every product V, okay, sold by the agency and therefore potentially subscribed to by a monoproduct customer, we want to find which additional product we should match with it in order to mostly motivate a monoproduct customer who has product V to buy it and become multi-product. Which kind of data do we have? Well, essentially, for every agency, we have two main information, okay? We know the behavior of the monoproduct customers. So in particular, for every monoproduct customer in every agency, we know to which product this monoproduct customer is subscribed to. So these are just categorical data, which has many categories as the total number of possible products that are offered by the agency, which is 15. And then we have the behavior of the multi-product customers. And we summarize this with a network for every agency, which is represented by an adjacency matrix, where we have the products on the rows and on the columns, so that every element in this matrix corresponds to a pair of products and will be either 0 or 1 if we do not observe or if we observe an edge among those two products in that agency. How do we define an edge? So we define an edge simply by, we draw an edge among two products if the total number of multi-product customers subscribed to those two products is greater than the 10% of the total number of multi-product customers subscribed to at least one of the two. Why do we do this? We do this because we want an edge to represent a true preference for matching two products. So we need to control somehow for the marginal preferences. Just to make you an example, I may have many customers buying at the same time, I don't know, pasta and milk, okay? But not because there is a true preference in matching them while cooking, as far as I know, but simply because they are popular, right? They are popular ingredients in the cuisine. So we want to control for this effect. But the key point here is that for every agency, we end up with a network. So we have multiple network observations. Now, with this data, if you think, each agency can already define its set of cross-selling strategies, telling for every product V which additional product I should offer for every agency. And in particular, if we define with AIVU, the random variable measuring the presence or absence of an edge among the products V and U in agency I, simply I will offer to monoproduct customers having the product V in agency I, the additional product having the highest edge probability with that product, right? Because this is measuring how much appealing it is, the highest probability of connecting, based on the data on the multi-product customers. And I do this for every product, and I end up with my set of cross-selling strategies for every agency. We can actually do something more, if you think, because we have also the data on the monoproduct customers. So once I have my strategies, I may want also to rank them in order to decide which one advertise more than another. And I want to rank them in terms of effectiveness at creating new multi-product customer, because this is what we wanted to do at the beginning. And if you think this quantity, this aspect depends on two quantities. First, the probability of an edge among product B with its best offer. The higher it is, the more appealing is this best offer to the current product. Okay? So this is somehow measuring the preference for matching those two products. So the higher it is, the happier I am. And then if you think there is another quantity, because it's actually the expected frequency of the monoproduct customer that I am targeting. Okay? So the more this quantity is measuring the total number of the expected frequency of the customer that I am targeting. The higher it is, it means that I'm targeting a big portion of my customer base with that cross-sell offer. So potentially I will have more multi-product customer if this best offer is effective. Okay? So we match with every cross-sell offer a performance indicator. The higher if this is high, it means again that we are targeting a sizable proportion of the monoproduct customer in my customer base with an offer which is very likely to be appealing to them. And this is the end of the talk, actually. No, I'm joking, but this could be the end of the talk, but there are two issues. It could be the end because we already have our quantities, we have our data, we can estimate them, we can end up with our strategies. But there are two problems. One comes from business intelligence, one comes from statistics. Because if you think, if I need to define, cooperate, coordinate, advertise different strategies for every agency, this creates cost for the company, right? At the same time, we are faced with statistical error in estimating the parameter underlying these strategies. And this is a particular product in estimating these edge probabilities, because if I do this for every agency, at the end of the day, if you think I have one parameter, edge probability among product V and U in agency I, and one observation. Is there or not an edge there? So if we don't borrow information or we reduce dimensionality, it's going to be, we are losing a lot of efficiency. So what's the idea? Well, we want to answer them all together. One idea is that we can do clustering, right? Because if I have a group of agencies that are sufficiently similar in terms of the monoproduct customer choices and the co-subscription behavior, maybe I can cluster them and give to these quantities the same set of strategies, right? And I can also use the data from this for all these agencies to estimate this set of strategies. So this allows me to improve efficiency, but also to reduce the cost, because I'm going from an agency-specific set of strategies to shared set of strategies. And if we look at the data, these are data for 3 agencies. For example, there seems to be some shared structure, right? So what we are actually doing here is not clustering, for example, nodes, but we want to cluster networks, okay? And if you look at the data, it seems that there are some shared strategies, some shared behavior among the co-subscription network, similarly for the monoproduct customer choices. So it makes sense, right, to cluster this data. And if we go like that, essentially we need three quantities to be estimated. First, I need the cluster membership, so I need to estimate for every agency in which cluster this agency is, okay? Once I end up with my cluster, I need to estimate within each cluster the probability of an edge among all the products, and I will use them to define my cluster-specific cross-sell strategies, and then I will need to estimate the expected frequency of the monoproduct customers associated to the agency in that cluster, because this will tell me the performance indicator associated to that. Just to give you an idea, this is what we want to end up with, essentially. So this is the case where we have 3 clusters, and we have 8 agencies. And every cluster is represented by 2 parameters that are important to me. First, this is a matrix containing the probability of the edge probabilities among the products, okay? And I will use this to define the set of strategies in cluster 1. These are the estimated expected frequencies for the agents, for the monoproduct customer associated with every product in the agencies in cluster 1. And I will use this to define the performance indicator. And then I know, for example, that agency 1, 4, and 5 are in cluster 1. So essentially, what I've done is use the data for these agencies to estimate these parameters, okay? Once I have these estimates, I will build up the same as before, my cross-sell strategies and my performance indicator, and I will give these strategies to these agencies, okay? They share them. Once we have this, we can go, but how do we get it? So the idea is that we want to take a model-based approach toward clustering. We do this mostly because we want to also try to quantify uncertainty, okay? Because we want to understand how much is reasonable, for example, to give to the agencies in the same cluster the same strategy. So we want to understand how much variability there is among the agencies that are in each cluster. But if we go like that, what we need to do is essentially for every cluster define a statistical model that is underlying the data for the agencies in that cluster. So a statistical model that is generating the data on the monoproduct customer and the data on the networks, okay? And I need, of course, to allow the statistical model to change across the clusters. So at the end of the day, essentially, and I want also that this statistical model is enough flexible. Why we do this? Because if I do not have an enough flexible statistical model in every cluster, I saw the question. If you have the same statistical model in a poor statistical model in a cluster which does not fit that much well the data, maybe this will force you to add more clusters. Not because there is a clustering structure there, but because the model is not enough flexible to represent the generative mechanism in a cluster. So what we want to do essentially, we have essentially to model two random variables in every cluster now. The first one is a qualitative variable. This is telling me the behavior of the monoproduct customers, okay? The second one, and this is the problem, is a network valued random variable. So this is a variable generating the networks for the agencies in cluster K. How do we model the mechanism associated with this variable in a flexible way? Is not so easy because this is a random variable, if you think, defined on a non-standard space. A sample from this random variable is a network configuration. So how do you assign the probability in this space? This is one of the main goal we will try to address. Okay, so as I was saying before, it's pretty easy to model the monoproduct customer choices in every cluster. These are categorical data, okay? So simply I need for every cluster a vector of parameter, has many parameters, has a total number of possible products, there is 15, and they are telling me the expected frequency of the monoproduct customer associated with every product in cluster K, okay? And then I need to allow this parameter to change across cluster, and I'm done. For example, if agency I is in cluster K, then the joint probability for the monoproduct customer choices of its own customer will be essentially the product of the expected frequency by the total number of customers associated with every product. So this is easy life. What about the network? So this is the problem I was telling you before. How do we model the probabilistic generative mechanism associated to a network? And why do we do this actually? We do this essentially because we don't have a single network observation, we have more of them, okay? So maybe we can see this data as a realization from a random variable defined on a network valued sample space, so that a sample is a network, and I can use this data probably to estimate the probabilistic generative mechanism associated to them. So we can go a step further compared to what is done when you have a single network. I mean, when you have a single network, what you can do is try to, for example, latent space model, ERGM. These are good models, but they are not enough flexible, but simply because they don't have enough network information to go over. It's like when you want to estimate the density of the weight of a person, but you have one data. So it doesn't make sense to try to do that in a flexible way. So just focusing now on how we build this probability mass function. So our data are available, as I was telling you, as a sequence of adjacency matrices. They are of dimension capital V times capital V. They are symmetric. And they have binary elements, so that the element VU in the adjacency matrix AI, which is equal to the element UV in the adjacency matrix AI, will be 1 if there is a preference for matching product V and U in agency I, and 0 otherwise. Now, this is building up some notation and start building up our random variable. Now, these adjacency matrices are symmetric, okay? So they are uniquely defined by their lower triangular elements. This means that if I want to build up a probability mass function for my network, I simply need to model the vector containing its lower triangular elements, okay? That I will call with L of AI. Let's build up the random variable. So where are these guys coming from? Well, they are vectors and they contain binary elements. So they are from a multivariate random variable with binary elements. But these entries are not unrelated binary variable. They are edges from a network. So there is a network type dependence down there that I want to take into account when building up this probability mass function. What is the sample space? So a sample is a network, okay? So the sample space will be simply the set of all the possible network configuration that you can have. And finally, I need a probability mass function that is associating to every possible network configuration the probability that I observe it, okay? What is the problem? How do we represent this probability mass function? And how do we allow this probability mass function to flexibly change across our clusters? It may be easy life at the end of the day, in our case, because we have binary edges, okay? So I have finitely many network configuration, right? So I can see my network value random variable as a categorical variable, okay, with a category for every possible network configuration. So to define the probability mass function, I simply need one parameter for every possible network configuration telling me the probability that I observe it. Once I have my data, I estimate these parameters and I'm done. Just to make you an example, if we have a network with 3 nodes, okay, I will have one parameter telling me the probability of the fully empty network. I will have another parameter telling me the probability of a network with where there is an edge among the first 2 products and 0 the other, and so on, blah, 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 blah. So I need 7 free parameters in this case to fully represent the probability mass function of a network, of a binary undirected network with 3 nodes. What's the problem? That the offer typically is much more complex than 3 products. So if we go as before, I will need 2 to the 105 parameter to be estimated if we go fully non-parametric as before. I'm even not sure there exist as many agencies in the world I can collect data from to estimate this probability mass function. On the other hand, as I was telling you before, the available parametric models are somehow too restrictive. I mean, I could say, for example, well, all the agencies in one cluster are generated from the same ERGM, or they are generated from the same stochastic block model, or the same latent space model. But this model is mostly developed for a single network, and we have done some analysis, and what you can see, if they are all generated from there, then this model will tend to collapse information around an average structure and tend to underestimate uncertainty. So you want something more flexible. So what can we do? We can do what we always do and what Horatio suggests when you have 2 very different ideas to answer the same problems. So try to find some kind of golden mean among them. Because what we want to do essentially is try to develop some representation that keep the flexibility of the non-parametric models, but it's much closer in terms of computational tractability for the parametric ones. And we do this developing a mixture of low-rank factorizations. This is actually an idea we draw from other papers that we had in neuroscience, where we had multiple connectomes collected on different subjects, and together with this information we know also if those subjects had or not a neurological disorder. And what we wanted to do is try to understand if the whole generative mechanism for the connectome was changing or not across these groups. And in testing them, we wanted to find some flexible representation. Now, if you change connectome with co-subscription networks, agencies with human, and clusters with disease, it's like the same, right? So this is what we want to do. Probably is not as much scientifically interesting as neuroscience, but there is statistics also in marketing. And if we help company to get more money in a fair way, they would probably pay more taxes, and the public institution can use to fund grants on neuroscience. So the final goal is to get more grants on neuroscience. So what I will do, going back serious, is try to build up now this random variable, step by step. So the first key step is the low-rank factorization mechanism. This is essentially the key one to reduce the dimensionality and borrow information across the edges. And I will show this mechanism to you by showing you how we generate a network from that. So the first thing we do is we take the products and we place them in a capital R dimensional latent space. So that every product will have a vector of capital R coordinates telling his position in this latent space and forming the rows of the matrix capital X. That XVR is the art coordinate for, it's not very original, it's product, of course. I had in mind brain neuroscience application here. So now, the rth column of this matrix is representing you the rth coordinate of the capital V products. And what we do is we multiply each column by a column-specific weight parameter that is telling me the importance of this dimension in constructing the network. And why this? You see in the third step, where for every pair of products, you construct a similarity measure among them as a function of their coordinates in the latent space. So, and we take the dot product of their latent coordinates. So that if two products have coordinates in the same direction are more similar than products with coordinates in opposite direction, then we map this similarity in the probability space using the logistic link, so that the more similar two products are, the more likely is that they are connected. And finally, we generate a network. How? Simply by sampling an edge or a known edge for every pair of products from condition-independent Bernoulli random variable given their specific edge probability. So this is essentially a constructing way of generating, it's very close to the random dot product models, right? Or the latent space model, where instead of having the Euclidean distance, you have the dot product distance, okay? And as I was saying before, this is not flexible, because if you assume that all the co-subscription network generated from this mechanism, then you tend to collapse information. So you want to have something more flexible. We were able to show that there are several probability mass functions for a network that you cannot represent with this mechanism. And the idea is quite simple, because what we say is, okay, instead of having just one low-rank factorization mechanism, we have capital H of them, okay? Each one having its own vector of edge probabilities defined by the low-rank construction, and each one having a different probability to be selected to then generate my network. So essentially what we are, if you're familiar with mixture model, this is what we are trying to do. So we are trying to represent the probability mass function using a mixture of latent space models. How do we generate the data from here? So as I was mentioning before, the first thing we do is for every subpopulation, we construct the edge probability vector associated to that subpopulation from the low-rank construction. And we are allowing this guy to change across groups. So the idea here is that the position of a product in the latent space can change across the subpopulation. Now what we do is we sample one of these subpopulation, okay, where nu H is the probability that we sample the subpopulation H. And once I am allocated in the subpopulation H, I generate a network. How? Again, as before, simply by sampling an edge or a known edge from condition-independent Bernoulli random variable given its own edge probability, but now specific to the subpopulation where you are. Okay, so this is just a constructive representation to tell you that we are going to represent the probability mass function of the network as a mixture, right, of the product of the marginal probabilities, where the probabilities are factorized as before. So this is simply a mixture of, see that as a mixture of latent space model. If you represent the probability as a stochastic block model, this is a mixture of stochastic block model, which allow you much more variability and much more flexibility in modeling this probability mass function. And actually we show that in this representation with this edge probability factorized using the low rank mechanism, you can potentially represent every possible probability mass function of a network. We do this using theory from tensor decomposition and singular value factorization. Okay, so we have a good model for the unconditional probability mass function. Now what we need to do is we need to allow this probability mass function to change across clusters. Okay, we need to go from modeling just the probability mass function of one network to K network, where K is the index of the cluster where you are. So we need to allow this probability mass function to change across the clusters. Again, the idea is pretty simple, because we keep the same as before. What we are doing now to allow the changes across cluster in this probabilistic generative mechanism, we take the mixing probabilities to be cluster specific. So now if you are in cluster K, the probability that you are assigned to the subpopulation H is no more common to everyone, but is specific to the cluster where you are. So it's nu HK. And this is the mechanism again. If Ci is the cluster indicator for the agency I, and assuming that agency I is in cluster K, then I generate its co-subscription network given that that agency is in cluster K. So again, I sample one subpopulation, where now the probability of being allocated to subpopulation H is specific to the cluster where this agency is. And then once I am in that subpopulation, I generate a network as before. because what you can see here is that I am allowing only the mixing probabilities to be specific with the cluster. The mixture component are shared across the clusters, right? The H here is not changing with K. And we do this because we want also to borrow information across clusters in modeling this probabilistic generative mechanism. Because we need to borrow information. These are huge probability mass functions, as we have seen before. And an interesting thing related to our application is that with this mixture representation, with cluster specific weights, the probability of an edge between products V and U in the agency in cluster K is available in a very simple way. It's just the weighted sum of the edge probabilities in every mixture component. This L is denoting the pair of products V and U, multiplied by the cluster-specific mixing probabilities. So it's very easy to get them. And because these are those that we use to define the cross-edge strategies. Okay. So we have essentially a likelihood at the end of the day. Now we need to do inference on that. And we do this taking a Bayesian approach toward inference. This is particularly useful, as we will see in a while, for the clustering mechanism, because Bayesian world, in particular the Bayesian non-parametric world, is full of prior for random partition that allow you the total number of clusters to be unknown and the cluster allocation to be unknown. So it's pretty convenient from that perspective, also computationally speaking. But if we trust this guy, once we have a likelihood, which is represented by the probabilistic generative mechanism for the monoproduct customer choices and the multi-product co-subscription network in every cluster, we need to define a prior for these quantities, and we do this by choosing prior for the elements in their factorization. We need also a prior on the cluster assignments. We will see this in a second. But once we have defined them, and once we observe our data, we simply need to update this prior and get our posterior. So for the cluster assignments, for the probability mass function of the monoproduct customer choices, for the network very random variable, and we will use this posterior to estimate our quantities for cross-selling and to understand where the agencies are allocated. I'm not going that much in detail on the prior choice. I just want to highlight some key ideas that we had in mind when choosing this prior. The first key one is that we want, of course, to keep the flexibility that we had in the likelihood. I mean, we played so hard to have some kind of flexible model. Now it would be quite silly if, when I define a prior over that, this prior is assigning probability 0 to some part of the space, because it's like going back to be less flexible. So from a Bayesian perspective, we want the prior to have full support in this space. Another nice thing, that we wanted to have was to have posterior computation available in a simple way through a Gibbs sampler. The model seems complex, but trust me, you have a Gibbs sampler. So it's an MCMC algorithm that updates the different parameters based on fully conjugate posterior updates. A thing that we use it here, which is very nice, many of us are working with binary edges. A nice thing here is that recently it has been developed a data augmentation scheme for doing Bayesian inference in a conjugate world, also in with the logistic link. So this is the polyagamma random variable, okay? So you augment the data. Once you have augmented the data, you can still update from that. I like the logistic link because it's the canonical link in the fragmentist world, so it's nice to keep that. It has nice interpretation. Another point is that we don't know how many mixture components there are. We don't know the total the dimension of the latent space, right? So what we did essentially is try to choose prior for the quantity control in this dimension that has some shrinkage effect, so that they allow somehow to avoid over-parameterized representation, but try to delete in an adaptive way dimensions that are not required to represent our data. And finally, clustering. So we will go now to that. Because the key point here is that we don't know how many clusters of agencies there are, and we don't know the allocation of the agencies to the cluster. So we want a prior that is somehow trying to help us in allowing uncertainty in this quantity. So we do this choosing a Chinese restaurant process prior. So this is a prior for random partition coming from the Bayesian non-parametric world. So the idea essentially is that you have random partitions, and then with this prior is assigning probability to this partition. If you are not familiar with that, a nice thing is that you can quite easily describe it in this way, essentially. There is a restaurant, okay, the mechanism to assign things to the cluster. There is a restaurant and there are many tables. Every table represents a cluster, okay? And the assignment to cluster is like people entering this restaurant in a consecutive way, okay? And the decision of a person to which cluster, to which table to sit, depends on the choice of those who entered before him. And in particular, under the Chinese restaurant process, people are sociable, actually, but there is some chance that they are not. I mean, so if under the Chinese restaurant process, if there are a lot of people in a table, I want to sit there. But there is also some chance that I don't want to speak with anyone, and that will create a new table. And this is allowing randomness or uncertainty in the total number of clusters. There's some nice properties, but what is important for us is that once an agency enters, it sits in cluster K, okay? Its data on the monoproduct customers and multi-product customer are generated from the two random variables in cluster K, and I will use the data for this agency, and all the agencies sit together with this agency to estimate this quantity, and I will give to the agencies in the same table the same set of cross-sell strategy, okay? And also this one allows us to develop some kind of simple allocation and algorithm for posterior inference. So let's go back to our data. We apply the model to the data, and then this is essentially a summary of what we get. So we estimate 20 clusters, okay? So we go from 130 agencies, okay, to 20 clusters of agencies. So from 130 possible different set of cross-sell strategy to just 20 of them, which is already a good reduction in terms of cost. Now this figure, this fancy figure, is a summarizing the cross-sell strategies in the different clusters. So here you have the different products. So these are the monoproduct customers that can have these 15 different products. Instead, on the right, you have the best offer, okay? Then, the dimension of every edge connecting a product subscribed to a monoproduct customer to an offer, okay, these are the products that appear at least one as a best offer. This dimension is proportional to the total number of clusters in which that best offer coincides. The color is, the blue is darker if the performance indicator is high, okay? And the dimension here of this box is proportional to the total number of times in which each product appears as a best offer. So what we can see here first is that there is not that much huge difference across clusters in terms of cross-sell strategies, which makes sense because we are working in the same insurance market, okay, in Italy. It's actually just from the northern part. So I don't expect huge variation in the different cross-sell strategies across clusters, but there are some difference here, which makes sense also to try to target better this offer. Another interesting thing that you see is that typically the products subscribed to a monoproduct customer are matched with a best offer coming from the same basket. I mean, the first 6 products are typically family type products, like house, car, injury, saving, investment, retirement, and they are typically associated with products from the same basket. The same you can see here for the business type ones. What we can see here is that the monoproduct customers having a car or house are typically better for creating new multi-product customer. Why? Because the house is very popular in the monoproduct customer choices, it's very popular in the family choices. Car insurance is compulsory in Italy, okay, because it covers third-party liability policies. So I have many customers here that I can target, right? And if we see here, the popular best offers are the offers on investment, offers on injuries and damage. And interesting, the offers on investment, if you see, is attracting customers, monoproduct customers who currently are subscribed to policy on saving or retirement plans, which makes sense, they have money, right? They may want to invest. The policy on injury is typically offered to monoproduct customers who are subscribed to policies on health or income protection. This gives you money if you cannot work because of illness. So it makes sense, right? These are health type policies associated with an L-type one. And the damaged one is attracted business policies. So this, I mean, the result made sense for us when we showed it to the insurance guys. They say they made sense, so we were happy about that. And this is just showing you the results. I mean, I was saying to you that I wanted also to quantify uncertainty in my estimates. And this is showing you the result for just one cluster. This is the most populated cluster. So here you have the posterior mean of the edge probabilities among the products. Here you have the posterior mean of the expected frequencies of the monoproduct customer in every product. This is a summary of the cross-sell strategy. So what we can see here essentially is that this is consistent with the result before, because here you see the community structure of the family type products that is consistent with this form of best offer. Here there is the community of the business type products. Another thing that we didn't notice and the insurance guy noticed is that here you have also two sub-communities. Can you see them? And the interesting thing is that product one, there are house, car, injury, and then you have saving, investment, and retirement. And these are actually the non-life and life insurance products. So it makes sense that they were even more connected. Another interesting thing is that here you have the first and the third quartile of the posterior distribution. And what you can see here is that we are kind of, the posterior distribution is quite well concentrated around our estimates, which, I mean, makes sense because we are borrowing information across the agencies, and therefore it makes sense to rely on this estimate to build up the cross-sell strategies. So just to sum up, what we have done essentially is to develop a model, to joint model and cluster together network value random variable and categorical variable. So this is some kind of different ideas because we don't need to cluster, for example, nodes, but we have multiple network observations that we want to cluster. So we are clustering networks and use these data to define cross-sell strategies. Another interesting thing of why we want to model the entire probability mass function of the network is that maybe I want to generalize my policy, my offer to multi-offer instead of a single one. And the idea is that I will offer to a customer having B the additional set of products that is jointly maximizing the probability of having an edge with it. And to estimate this guy, you need to have a joint probability mass function for the edges, as you can see. And to get it, once you have the model for the entire, you can just marginalize out those that you are not interested. We can do a lot, of course. One thing is, how do we generalize to weighted network data? Maybe there is much more information there, and it's much harder because now I can define it a flexible way because I have finitely many network configuration, but if they are weighted, maybe infinitely space. So it's much harder to, I mean, at least to build up theory for that. Compared to the one. And then, of course, we didn't consider cost of prices, which is an important, of course, thing. This is all. Thank you for the attention.
Okay, questions? Yep.
Thank you for a very interesting talk. I've just wondered, when you look at your network, so if you just cluster them first without doing the mixture model, and then fit a model to each of the individual clusters, would you get something very different?
So you mean I cluster the network first, and then I fit a separate model there?
So you apply a network clustering algorithm to cluster your set of networks into different networks.
So in terms of clustering, how would you cluster this? You would compute like a distance among the matrix of the distance among two matrices, like the edges, and then cluster them. So we haven't looked at it because one thing that we wanted to do was also to borrow information across the clusters, because we're trying to model a quite big object in terms of probability mass function. So we wanted also to try to borrow information across the different clusters. In this case, we do that by keeping fixed the mixture component. Okay. So if two agencies are in a different cluster, they may share the same mixture component in the mixture representation, and this allows me to borrow information across that. But we haven't looked, that one may be an idea, first cluster and then estimate a different model, but we wanted to do, go obtain more information by borrowing strength also across the cluster.
Yeah, but you also introduce more parameters that way.
I don't think so, because if I estimate, if I cluster them and then I estimate, So within each cluster, would you estimate, like, I don't know, a stochastic block model, or?
Perhaps.
But okay, but maybe that then in that cluster you're not characterizing that much better the uncertainty.
We can talk about it later.
Okay, yeah, it would be interesting.
Okay. Yep.
Thank you for your presentation. I was wondering, before you start analyzing your networks, you actually reduce a bimodal network to a, well, one-mode network. You go from customers and customers and things that they can buy to things that they can buy against things that they can buy.
Yeah.
Have you considered, or I don't know how many customers are in your sample, but those are the people that you want to target probably, and have you considered including their information or modeling it in a bio?
Yeah, so you are suggesting, I mean, not looking at the problem from a network perspective, or
Well, a different network.
but where the nodes are the customers?
Customers and
A bipartite network. Okay. So what we somehow collapsed that, because what we wanted to do is, so the multi-product customer in every agency are not that much. They are like around, they were about 300, 500. So, and they can be like associated, so, and the total number of possible configuration of products that they can have is 15 times 14 over 2. So it got quite sparse. So if we wanted to estimate the probability there, we didn't have that much data. So maybe we could get kind of consistent and efficient estimates for some co-subscription and very pure one. Instead, if we are trying to borrow information across them, we wanted to, draw information also from the others. That was the main point for doing that.
Yep.
Yeah, you say you're borrowing information within clusters, but by clustering at all, are you not sort of throwing away information? The clusters are slightly wrong. You're not using information in the other clusters. So,
in which sense? So you are suggesting that I shouldn't borrow information from other clusters?
I mean, my cluster at all, did you compare it to not using clusters at all?
Well, I mean, I want to do cluster. The point is that, I mean, I want to reduce the number of policy, the strategies to reduce the cost, and I want to do clusters. And once I have to estimate the mechanism, now the data in this cluster are quite complex objects, so it makes sense that I'm also borrowing information, but I am allowing changes across. I mean, the important thing is that I am allowing changes across clusters. And if I borrow information to estimate the mechanism there, it's maybe.
Yeah, I mean, if one agency sells one set of products, another agency sells another set of products, they might be very different, but they might share some products that they both sell. And by sort of analysing them differently, you're perhaps throwing away the information that the ones they do sell.
I don't got the point on which type of information in particular I should borrow.
I'll talk to you later.
Okay.
Maybe just a quick follow-up on that and the previous question as well. I mean, indeed, you are before even starting, you actually define the kind of network A by doing a cutoff, which is rather arbitrary, right? So you, or at least
the 10%, you mean? So okay, so to.
Why would you do that if you cannot simply? I mean, you could very simply just include a size effect into your logistic model that actually accounts for how big the actual.
So you mean the cutoff in terms of from going from weighted to binary, that one?
Well, basically, observations are just observations very similar to what Mirko was doing in the last talk. Basically, observations on links, and you just model them by some probability, and you just have counts on each of the links.
Yeah, that one would be, I mean, modeling the weights will be like the next step to do that. The cutoff, I mean, from an applied perspective, the agency liked, I mean, they liked this type of thresholding, and they got better, like, there is or not a preference in terms of how much preference and the probability of that. So it was kind of a simple starting point for getting it, but of course, I mean, we are throwing out some information there.
Maybe a good moment. Well, Stephen Sennon called this diatom, and he called it disease, in which basically everyone tended to kind of take continuous data and discretize it into two levels. He said doctors suffered from it a lot, but maybe also insurance companies, you never know. Anyway, thanks very much for an inspiring talk. Let's thank